Okay, section 2.4, inverse functions. So the inverse function simply undoes the action of the original function. So it performs the opposite action, the opposite operation of that original function. So if you've got the original function is f of x, the input, which is the domain of that function, is fed into the function, and you are going to get the output, which is the range. Now, that range now becomes the input of the inverse function. So the inverse function will take whatever the output of the original function was, will take it back to the original set of values, so the x's. We are going to, however, change the notation. So first of all, the inverse function looks like f with a floating -1. You might think mistakenly it's to the power of -1, but you've actually seen sine inverse written on the calculator key in the same way, so it just means it's inverse function. Now the input of the inverse function will be that set of values, but for that function we will call it x, and it is going to be the input of the inverse, and it's going to be its domain. Then it goes in and undoes the action of f of x, and the output, which is going to be called for that function its y values, it's going to be the range. So what does it do? It swaps the domain for the range, and the same the range for the domain, and swaps x's with y's, so the role of x's and y's are switched. So that's the effect of applying the inverse function. Now when you sketch the graphs of the inverse function, because effectively you are switching the role of x's and y's, you will obtain the graph that is, let's just have a look. So if that was, if my f of x was a straight line, then this value here, the y-intercept, I called it a, would have to now be on the x-axis, and the value of b here would have to go on the y-axis. Okay, it's going to be negative, but I'll call it b. So you are going to get the reflection in the line y equals x. So all the x's and y's are switched with each other, so graphically you're going to reflect y equals f of x in the line y equals x to obtain y equals f minus 1 of x, so the inverse of f. What's really important to note is that if your graph has any points common with the line y equals x, like over here, that means this point will actually will be common to both the inverse and the original graphs, and obviously the line y equals x. Okay, so the domain, let's just write it down, of f of x becomes the range of the inverse function, and the range of f of x, so your y's, these are the values that become the domain. So they will be changed to x's of the inverse function, the domain of the inverse function. Let's actually have a look at some examples where you've got to find some inverse functions. So over here in the example 13, our function h of x is 2x squared minus 7. Now it's defined for x is greater or equal to 0. So this is the domain of f(h) of x. We are asked to find the inverse. So the inverse function is going to be found by undoing the action of this function. So the best approach is to, let's write y instead of h of x to begin with. So define it. There you go. The best thing to do is simply switch the x's with y, because what we're going to be doing, we are going to be undoing whatever happened to the x's on that side, and then you're going to end up with x on its own. So if we switch the x's with y, as we saw in the previous slide, that's what happens when you find the inverse function, then all you need to think of it is make your new y the subject. Okay, so the first thing you do is to switch x's with y's, and the second thing, make y the subject. So we are undoing, taking away 7 by adding 7, then undoing multiplying by 2 by dividing by 2, and then square rooting. So y is equal to plus or minus square root of x plus 7 over 2. Now that would be the proper answer, but we've got x is greater or equal to 0 originally. That means because your x's are swapped with y's, the range must be y is greater or equal to 0. So that means you can only take the positive answer, because it has to be positive or equal to 0 at its lowest. Now, you've been, so if that's the range, let's find the domain. So the range is that, and the domain. Okay, so for the domain, we're going to look at the original function, so y equals h of x, and find out what is the range. So for the domain, so we need to check the range of h of x. So this is a quadratic, and as I've shown you before, with a quadratic function, the best thing to do is always to sketch it. So this is a quadratic function going through -7. It's a smiley face, but this one is defined for x is greater or equal to 0. So we only have this branch. Okay, so that tells me that the range is, the lowest value is -7, anything above -7. So the range is y is greater or equal to -7. So that makes the domain of our inverse function. You swap the x's with y's, so it's x is greater or equal to -7. So that is the domain. Okay. Okay, question, example 14, you've got the reciprocal function, 3 over x minus 1. So we're going to follow these bullet points. We're going to switch x's with y's, but define your y, because they haven't called f of x as y, so just make sure you do that. So originally we've got y equals 3 over x minus 1. Let's switch. So switch. We're going to get x is equal to 3 over y minus 1. And now make the subject, so y the subject. So we are going to multiply by y minus 1 and divide by x. So y is equal to 3 over x plus 1. There's our function. Now, what about the domain and range? So this is the inverse function. Now, the domain of the original function becomes the range. So the range, you just need to switch x's with y's. So now you've got y belongs to real values and y cannot be equal to 1. So that is the asymptote. So for the domain, we are going to check the range of f of x. So with a reciprocal graph, if you remember from when we tackled reciprocal graphs, always sketch it. So the reciprocal graph that we are given is 3 over x minus 1. So 3 over x would just have 2 branches here, just like 1 over x, just slightly more stretched. Minus 1 in the denominator means the asymptote is at 1. It's been, the whole graph is shifted, so it looks like this. So 1 to the right. This value can be found very easily by making x equal to 0. So it's going to be 3 over 0 minus 1, which gives me minus 3. Okay, so this is that point. Not that we need it for this, to answer this question. So what is the range of this function? So there was no restrictions on the original function apart from the asymptote. So we've got the whole 2 branches. So if you go up, the only value you're not going to obtain is y equals 0. So the domain, so the range of the original function is anything apart from y equals 0, and that becomes the domain. So the domain of the inverse function is going to be x's belonging to real values apart from 0. Right, moving on to example 15. F of x is equal to square root of x minus 2 when x's are greater or equal to 2, because you couldn't have a square root of a negative answer. The other values would make the x minus 2 negative. So what is the range of this function? So the range, you can actually either sketch it. If you remember that the sketch of this function is, well, square root of x looks like this. Square root of x minus 2 is simply starting this from 2. So it looks like this. Okay, so you've got that. Alternatively, you could just put some values in the calculator, put a very big value of x into this, and you will get a really big number. If you put x equals 2, you'll get 0. So you can see that you get anything from 0 upwards. So the range is y is greater or equal to 0. You can also use f of x is greater or equal to 0 because y is your f of x. Now to find the inverse, we are going to switch. So if you let y equals f of x, we're going to switch y with x's. So switch. So you have x is equal to square root of y minus 2. So let's undo it by squaring. So x squared is equal to y minus 2. So y is equal to x squared plus 2. Okay, so now we need to find the range and the domain. So the range is going to be very easy because the range is simply the domain of the original function, but we're going to switch the x's with y. So range, the range is y belongs to real values and y is greater or equal to 2. And the domain is easy as well because we've done part A where we found the range of the original function. So the domain will be, remember, your y's now become x's. X is greater or equal to 0. Obviously, x belongs to real values is also true. Now we are asked to sketch both functions. So x squared plus 1 for x is greater than 0. So, sorry, x squared plus 2. So it will look like this. There you go. And then the square root of x minus 2 is looking like this. And you can see that they are perfectly, should be symmetrical around y equals x line. So this is the invert, no, this is the original function, f of x, square root of x minus 2. And this is the inverse, f minus 1 of x is x squared plus 2. Okay, we're not asked to solve anything else. There you go. There's no point of intersection with y equals x. So the example 16, which is the final example of exercise 1D, we've got the quadratic function defined for x is greater or equal to 0. That's the domain that will become the range of the inverse function. Now, as you can see here, if I sketch that, this is normally the quadratic goes like this through -3. This one will start from -3 upwards here because we've got positive values here of x only being able to applied. Right, so we're going to say let's y is equal to f of x, be equal to f of x. Right, so we now have to swap x's with y's and make y the subject. This is going to be also only positive, not plus or minus. We need to reject the minus because we only have one branch. Okay, so we could see that the range of this, the domain of that one becomes the range. So the range is greater, values greater equal to 0. So you only choose the positive. Now the range of this function is, the original function is y's belonging to real values, but y's are greater or equal to -3. So the domain of the inverse function will be x's are greater or equal to -3. Both x and y are real values. We've got to sketch the inverse function, so you can actually sketch it. And I've already stated the domain, but I will restate it. So remember, if you can sketch it from this graph, that would be great. So -3, it used to go like this. So that was -3. So remember this, the x's and y's switch the role. So -3 used to be marked on the y-axis. Now you need to mark it on the x-axis. Whatever this value is, we haven't worked it out. It should be √3, I think. That will have to be swapped onto the y-axis. So it's √3. So here's the graph. So that is y equals square root of x plus 3. The domain, we could see even from the graph, the domain, we already found it, x's belonging to real values and x's are greater or equal to -3. Now finally, for part C, this is a really important method that you need to memorize. Then when you ask to find the solution to f of x equals to f minus of x, because you are effectively looking for points of intersection of the two graphs, f of x and its inverse. Now, if we mentioned before, when I sketched the inverses and the functions before and the line y equals x, these three graphs always intersect on the same point. So wherever the inverse and the original function intersect, the line y equals x will also intersect this point. So rather than trying to solve x squared minus 3 equals to square root of x plus 3, then you would have to undo the squaring. You will get quadratic to solve. Not a good idea. So a better idea is to just find the point of intersection of one of the quadratics, one of the functions with y equals x. So I'm going to find the intersections with f of x equals x squared minus 3 and y equals x. So replace your f of x with x, and we are going to solve this equation. It's a quadratic. I think this one will be nicely... no, you can't factorize it, so it's a half. I'll do the completing the square. You can use the formula. So it's x minus a half squared is equal to 3 1/4. So that's going to be 13 quarters, giving me x is equal to a half plus or minus square root of 13 over 2. So this corresponds to 2 values. Now you could see that we are looking for the intersection with this graph on the positive side. There will be another one on this side, which we're not interested in finding, so we want to choose the positive. So reject the negative value and you pick the positive. So 1 plus root 13 over 2. And that is the solution, which takes us to exercise 1D.